Okay, let's start. All right. I'm really happy to have Jing-Ze for today's Friday lunch seminar series. He is the final year PhD student at the Master Planck Institute for Astrophysics for MPA, Germany. Roughly 1 year after I started working at MPA as a fellow, he joined the same group, same as the mixed group, as a PhD student, and since there I saw, basically I watched him grow from a new PhD student to, I think right now is a very excellent independent. His research areas are really broad, ranging from transients such as X-ray binaries or tidal dispersion events, massive stars, mass transfer, and so on. Some of which we actually used to work on together. What impressed me the most about him is his persistence in pursuing project ideas that he found very interesting. Although his supervisor considered initially some of those projects perhaps overly ambitious. I think today we will, of course, I just want to make sure, students in the room, I'm not saying you should not listen to your supervisor. You should, but sometimes if you find a very interesting idea that you can convince your the supervisor into, then the projects might turn out to be really great projects. And in fact, today's talk is actually about one of those projects that might have looked overly ambitious, but ultimately carried it through successfully. Okay,
thanks a lot, Theo, for the wonderful introduction. So today I'll talk about these rings and quakes in these 3D massive stars. Let's see if this works. Okay, so I'll mainly talk about these two messages. The first, that inside the star envelope, the convection really looks like descending plumes and not really the circulating blobs we normally think of. Yeah. I don't really see that on my screen, so I'm not sure. Oh, it's in front of it. Yeah, looks like it's another screen. I'm not sure. Right. Drag. Get out.
Behind.
Yeah, sure. Maybe just hide the titles. Sorry about it. And the second message is that in the most supernova, we see that they interact with their surroundings. We think now that these materials are actually bound material instead of a steady wind, as most people assume. So first, let's take a step back, and the title says 3D massive stars in observations. The general idea is that if you look at the HR diagram and you start to look at our own sun, then you start to see some 3D structures on the surface. But overall, it's still kind of a fairly symmetric object. So you can sort of treat it just as a 1D object, and you can simulate it pretty safely. But as you go to these more massive stars, then you start to see this trend where they seem to be no longer 1D objects, especially if you look at their circumstellar surroundings. And it means you cannot treat them as spherical cows anymore. They are like real cows. They have ears and they have legs, and sometimes you can see they kicking their legs in observations. So this is why we care about them, but most importantly, these are basically the progenitors of all the transient and gravitational wave sources we see. For example, they will explode in different types of supernova and sometimes give birth to gamma ray bursts. And these most massive stars will probably just directly collapse into black holes. And if they find each other in the universe, they will start to spiral with each other and emit gravitational waves. So this is why we really want to understand these massive stars, especially in 3D. So why can't we just simply simulate these massive stars in 3D simulations for basically decades? It's basically this multi-scale challenge we have to face in computational astrophysics, that if you simply think about the different timescales you have to deal with in these stars. So let's forget about the nuclear timescale for a moment. I just look at the thermal timescale and the dynamical timescale. And for our sun, you have this 12 orders magnitude difference between these two. So this is basically a general agreement inside the stellar community that is completely hopeless to try to simulate the whole star in 3D. So does that mean that we cannot advance this at all? The answer is no, because if you look at these more massive stars like Betelgeuse, which is about 10 times more massive than our sun, and 1,000 times bigger than our sun. Then if you look at, for example, the thermal timescale in the envelope and the dynamical timescale, they actually become quite comparable. And the simple argument is that the Betelgeuse is much brighter than the sun and also much bigger. So you kind of push these two timescales together. So this is why that in recent years, we can start to simulate, especially the envelope of this object in 3D. For example, this is a group led by Jerry Goldberg and Yanfei Jiang at CCA. They try to use Athena++ to simulate the outer envelope of these red supergiants. And I have been involved in this other team called Cobalt, where we try to simulate the full sphere convective envelope of these stars. But you can see in both of these simulations, you have this black region at the center of your star, which is basically missing in all of these simulations, which is the bottom of the convective envelope. Okay, you might argue that this is not super important for the star itself, but actually when you start to think about how the convective structure develop in the stars, and also you have all these waves that are bouncing inside the star, then if you only simulate, for example, a wedge or the surface of the star, you are basically limiting the space that these waves and convective structure can grow in your stars. So this is why we really want to get to simulate sort of the whole envelope of the star. But why can't we just simply simulate this? It's because if you look at the local dynamical timescale at the bottom of your convective envelope, then it's still 7 orders of magnitude lower than the thermal timescale. And mostly what current standard code can do is just simulate some timescale in between. So how can we really do this? How can we bridge this, which is about 1,000 times beyond what the standard code can actually do? So this is why about 2 years ago, I started to look at how people simulate galaxies. And there, for example, this is a cosmological simulation from illustrious Jing-Ze. And there they always need to deal with this multi-scale problem where they have this whole large scale gas that is falling into the center where they form their galaxies. And there they have this unique code called AREPO, which is a moving mesh image decode. The general idea of this code is that it has a weird structured mesh, which is not something you normally see in computational simulations. This mesh is called a Werner mesh. And another feature is that as you start the simulation, you can think about this as a rotating galaxy or rotating disk. Then, as you start the simulation, the mesh actually goes with the gas. And this is very important for us if we want to simulate, for example, outflow from our central stars, where we really want to trace these outflows further away from the star. And another feature is that it has this function called local timestamp, which means different part of a simulation can take different timestamps. And this is especially powerful for stars, which is something I think most of the stellar community hasn't realized yet, is that if you go to the center of the star, the density and temperature become so high that you can only afford to use a very small timestamp there. For example, if you use 1 second at the center of your star. But as you go to the surface of the star, the density and temperature becomes more bloated. So you can actually afford to use a much higher timestamp there to evolve your system. And if you can balance this well, you can really save a lot of computational time. And just to give an example, one of my simulation takes about 3 months to run. You may think this is a lot, but if you use the same setup, but you push all these cells to the smallest timestamp you have, it can easily take 8 years to run one of the simulation I'm running. So that basically means I'm spending the whole PhD and probably 1 or 2 postdocs just trying to run this single simulation. But what's missing in AREPO, especially if we want to start to simulate the stars with them, is an accurate radiation transport. Why is this important? Because we care about near the surface of the star, you have radiation that's kind of trying to escape from the photosphere of your star. And that is where you really need an accurate radiation transport. But on the fly radiation transport, especially in 3D simulation, is pretty hard. And just to illustrate this, this is basically a simple test where you have 2 luminous sources shedding light onto an optic cloud in the middle. And what you expect from your daily life is that behind this cloud, you should be able to cast a shadow behind. But if you use most of the radiation transport method on the market, you get completely wrong result. For example, with this diffusion approximation, you basically approximate the radiation transport as a diffusion process. And in the end, what you get is that all the radiation just completely fills this shadow. So you don't get this shadow anymore. And if you use this method where they try to approximate radiation as a fluid, then between these 2 luminous sources, you're actually clashing these 2 radiation fronts together that creates this artificial radiation wall between them. So this is not something you want in simulations, but this is actually most of the astrophysical code can do so far. And so far, there's only a handful of code that can deal with this problem very accurately. And about 2 years ago, what I did is I tried to move AREPO to this accurate radiation transport list. And there I developed this implicit discrete coordinate radiation transport. The basic idea is that now in AREPO, you have this unstructured mesh, and you also try to discretize the radiation field in different directions. And normally we use 80 different directions to cover the full pi solid angle. And you ask, what is the intensity along this specific direction? And to solve this, you just solve the radiation transport equation. And the way we transport photons within our computational domain is that you know the intensity from your neighboring cells. And the way you transport radiation out is just that you exchange fluxes between your neighboring cells to transport out or in the radiation field. And it turns out this is quite affordable to do. And the main idea is based on Yanfei Jiang's method back in 2021. And this is now the main radiation module they have in Athena++ and Athena K. But I generalize this method to support this moving unstructured mesh in AREPO. It supports this local timestamp. It also supports a general equation of state. And the cost of this is actually quite affordable to do. It's about 50% more expensive than pure hydrodynamic simulations. So that means with this method, we can actually combine the multi-scale capability with AREPO with this accurate radiation transport method, such that you can actually open up a lot of possibilities to simulate all of these complicated systems in 3D. And for me, I come from this group where we are interested in massive stars. How do we actually set up a star in AREPO? The way we do this is that we take a 1D profile from 1D stellar evolution code, and then we take out the inner 3% of the star, because the core of the star is still too dense to be simulated in 3D. And then we replace this core with basically a point mass at the center, and we apply a constant luminosity at the center to heat up the star from below. We map this into 3D, and the whole simulation box is actually 300 times larger than the star itself. So we don't have to worry too much about the boundary effects. And these are just some technical details. One of our simulation takes about 1 million CPU hours to run. And with this, we can actually achieve for the first time to simulate the entire convective envelope. And just to show you this is a 2D slice of the convective pattern in my simulation. And this is the inner boundary you can achieve in Asina++. And this is the inner boundary you can achieve with this other code I used before. And this is what we can do now with AREPO, where we actually try to simulate the whole convective envelope in our simulation. So with this, I built a small grid of these 3D dying massive stars. And this is just an HR diagram showing you the location of the observed red supergiant on this HR diagram. So you see these are pretty cold on the surface, about 4,000 to 3,000 Kelvin, but they are much more luminous than our sun. They're about 10 to the 5 times more luminous. And this is where my 4 simulations lie on this diagram. So this is basically trying to probe the parameter space with a limited grid. And this is what they look like in my simulation, where I try to predict like a bolometric intensity map from my simulations. And you can see for these 2 simulations, they basically look like a scaled up version of our sun. They have a convective envelope, so that is why you see the convective cells on the surface. But if you look at these 2 stars, which only has about several hundred years before they blow up a supernova, they actually look quite different. And this is especially true if you try to look at the movies here, where you see the convective cells moving on the surface. But for these 2 stars that are just about to blow up a supernova, they actually start to develop this instability in the envelope that drives a large amplitude pulsation in the envelope. So first, I will focus on these stars, where they look much closer to our sun. And there, the question we want to ask is that, okay, what does convection actually look like inside the stars? And convection is this general phenomenon in astrophysics that you have convection going on in the planets, in the stars, and also sometimes in the accretion disk around supermassive black holes. And normally when we think about convection, we think about our daily life experience where you try to boil water and you have these blobs that rise and sink. So this is kind of our textbook view of convection. So you have this locally circulating blobs that rise and sink again. But this is not what we see in my simulation. So this is my tensor mass simulation, where you see the orange colors means the temperature fluctuation near the surface. And red means it's kind of going inside the envelope, and blue means it's going outside. And if you look closely at how this convective pattern actually changes in the simulation, you don't see the locally circulating blobs. Instead, what you see is that you generate some plumes that start from the surface, they merge with each other and actually penetrate all the way to the bottom of the convective envelope. And this is something that people speculated before that our conventional picture of convection works is not really what we see especially near the surface of the stars. And this is something that people already see in solar convection simulation, where they also see that they start to generate this sort of small plumes near the surface, and they merge with each other and actually penetrate very deep. And the physics behind this is that this convection is not really driven by heating source from below. Instead, it's driven by a cooling surface near the surface of the star. And there, the cooling becomes so intense that you actually compress the gas in this thin layer. And it compresses so much that you actually generate a density inversion, that the surface density becomes denser than your bottom. And if this happens in 3D, you start to have really tailored instability that generates these finger-like structures that try to penetrate through the envelope. So an interesting question in the future to ask is, okay, what kind of dynamo would you expect to generate from this? Because this is different from a sort of isotropic turbulence. this is really non-local, very large-scale structures. So you would expect that the dynamo generated from this is also different from an isotropic turbulence dynamo. And maybe this is kind of a generic phenomenon because we see this in this 10 solar mass massive stars. We see this in our sun. So this may mean that this kind of generic phenomenon that may happen in all of these stars or even planets with surface convection zone. And what will be the observational consequence of this? One thing we thought about is that we look at how the surface convective granules move on the surface. And this is again the intensity map, where if you look at this movie long enough, you can start to realize that the surface granules sort of move in groups. And this group motion are actually dominated by this like larger scale cellular expanding motions on the surface. And just to summarize this in this cartoon, it looks like the convective granules on the surface are actually dominated by, their movement is dominated by a larger scale motion below, inside the envelope. And this is something also observed on the surface of our sun. It's called supergranulation in our sun. And in solar convectivity, people have been debating whether this is simply a phenomenon arising from the convection itself, or it has something to do with rotation, because in our sun, the sun is also rotating. And the idea there is that you have rotation that kind of rolls up these large convective cells and give rise to this larger scale convective motions. But in our simulation, we don't include any rotation. We don't have magnetic field. So that means this phenomenon in our simulation can only arise from the convection itself. And this is quite interesting if we want to observe these stars. And this is a kind of a future prospect for future interferometry, where the prospect there is that if we can have enough spatial resolution in interferometry observations, then we can actually start to trace the movement of these surface granules. And that gives you an idea of what is the length scale of the deeper convection inside the stars. So this is another way that we can just look at the surface of the star and try to figure out what's going on deeper inside. And indeed, the observers are already start to do this, where they try to take images of these supergiants in a sequence spanning several years. And they indeed see the convective cells movement on the surface. But the general prospect for the future is that if we can get high enough spatial resolution in these interferometry observations, we can sort of try to approximate this real surface instead of these large convective cells you see on the surface.
What star is that?
So this is a red supergiant. I think it's roughly 10 to 20 solar masses. And people have also been doing this for more lower mass stars, like 1 solar mass red giant. They also can do this for some nearby red giants. So the future is that with VLTI, Chara array, or ALMA, if we can increase the spatial resolution of this instrument, then maybe we can actually start to do this and use these surface signatures to probe what's going on deeper inside. But now let's move to this more violent stars. And the question we want to ask there is that these are the direct progenitors of the supernova. And before 2010s, in supernova convectivity, we always think that the stars just blow up in near vacuum. There's nothing around. But after 2010s, actually, we start to realize these stars blow up in this dense, confined circumstellar material. And the reason we find this is just that we have better observational techniques that we can actually start to probe what's going on in this supernova very early on. And this can actually be a significant fraction of the supernova. And normally what people think or assume is that somehow just before the stars die, you undergo this erupting mass loss phase where they sort of have this enhanced mass loss just before they die. And if you try to fit a mass loss rate to all the observational signatures have, you can get a fairly large amount of mass loss rate, like 1 solar mass per year. And you can imagine if you lose your mass at this rate for 10 years, you lose the entire star. So this can only happen just before the star die. Otherwise, you wouldn't see them at all. So this is quite puzzling, that why the stars will just suddenly decide to have this enhanced mass loss just before they die. So what I propose from my simulation is that this is not a wind. Instead, this is a bound material. So for example, this is one of my simulation where you again see the central star, but now around the star itself, you see this bluish color, which means the density contours of the material around the star. So what I see instead is that just before the star die, it develops this large amplitude position. And during each position, it leaves some of a stellar material to its surrounding. And later on, most of this material actually falls back onto the star itself. And over time, this actually develops into a quasi-static envelope around the star itself. And you can also see that because of the large scale convection going on in the envelope, this surrounding of the star can actually also be not spherically symmetric.
What are the time scales?
The time scale of this position is about 1 year or 2 years, depends on what type of stars. So in principle, this
Per
is,
frame,
sorry,
per frame. So
what do you mean per frame?
what? The time is.
Yeah,
Oh, okay.
yes.
Still.
So the whole simulation is about 70 years, and each position is about 1 year or 2 years. Yes. And if I still have some time, I want to show this. And the people on Zoom cannot see it. Okay. Does this work? No. That I'll show you later. Okay. Sculpture. Good. So the idea is that we can try to compare this with observation, because in observations, they can try to constrain what is the density profile outside of the stars. And this is just showing you a density against the distance from the center of the star. And this is one of their observed supernova where they try to infer what's the density there. So you can see at least like our simulations can explain this supernova, but not really the more extended material for this supernova still. And I can make some testable predictions for future observations. So what I predict is that most of these supernova progenitors should have this large amplitude position just before they die. And this should show up in their light curves if you observe them just before they die. For example, this predicted light curve from my simulation. And what I also predict is that all of them should have this highly confined material around them. So far, there have been some observations of this type of events. For example, this is a 2023 XF, where they really see the progenitor of this supernova just before it explodes. And indeed, if you see their light curve, it shows this kind of variability. And this confined circumstellar material is also observed in this particular supernova. But these observations are so far quite sparse. And what I predict is that these observations are only the tip of the iceberg. We should be able to see this in most hydrogen-rich supernova. And you may ask, like, why haven't we been able to see this so far? And the answer is just that we are limited by our observational techniques. So to test this, we really need a decade-long monitoring of these stars, because we don't know, like which of them will go supernova in decade. But this is really a task for LSD, which is supposed to start operating later on this year, where it provides this decade-long monitoring for all of these stars. And hopefully among them will be lucky enough that some of them will blow up in next 10 years. And maybe if we look at the archive data from LST, we can try to look at whether they really have this position or not. And to test whether they really have this highly confined material around them, we need to take supernova spectra just several hours after they blow up. Because from the supernova spectra, we can see some emission lines. And this emission lines means there are some dense material around the star itself. And through the time scale of this, how long this emission line actually lasts, we can infer what is the spatial extent of this dense material around the star is. But so far, this is very hard to do because you need to capture the supernova early on. You need to send the alert to other spectroscopic people. So this is so far very hard to do. But in the future, in future 5 years, there are these UV missions coming up. One of them is called UltraSat, which is basically a UV telescope that can capture the shock breakout very early on, like within several hours, and send alert to all of this ground-based instrument or to this UV spectra called UVEX, where they can really try to test these predictions. And this is only the beginning because we have some other plans to try to probe these 3D massive stars, transient and binaries across the Hertzsprung-Russell diagram. So the general idea is now we are simulating this red supergiant. We're looking at their pre-supernova activity. So this is where we're now. But in the future, we actually want to expand this grid to other types of massive stars. For example, I have a test simulation for this blue supergiant, which is hotter than this red supergiant. And there we want to ask the question in observations, for example, in TESS telescopes, which are telescopes that try to observe planets. They also see variability in this blue supergiant. And we want to explain this. We are also going towards binary mass transfer. And in the future, we have some plan for tidal disruption events. And this is a plan not only involving people from MPA, where I did my PhD. We also try to collaborate with people who have different expertise in different fields. For example, we have Andrea Chiavasa on board, who is an expert in 3D red supergiant simulations. And we have this other professor who I don't really know the name, but I believe most of the people here knows him. And hopefully together with his student, he's going to explore the tidal disruption front. And over the years, I have been discussing different ideas with different people, whether we can use this to simulate, for example, proto-neutron star convection, transient in binaries. I talked with this morning about how we can use this for quasi-stars. So that means we really have a lot of things to do in the future. And hopefully we can get some of the list done in future several years. Thank you, and happy to take questions.
Very good to see pictures of very nice looking guys here. Any questions?
Yeah, if there's such a lot of mass loss before something goes supernova, presumably this is going to affect whether you get a neutron star or a black hole. Do you have any comments?
Yeah, I think the general idea in the community now is that this wind mass loss, if it is true, it can only happen for a very short time. So the mass you lost will still be like a small fraction of the total mass of the star.
So you see one solar mass per year.
Yeah, but for like several days, then it's still quite subdominant. Yes.
I have two questions regarding your two different scenarios. One is for the sun-like star, and another is for the massive star. For sun-like star, like you have simulated the whole convection flow. Now for solar, solar time, it will be a 24-year cycle, and many of the dynamo models predict there's something called meridional circulation from convection flow to the peak at the top of the radial zone. So do you see any kind of large scale motion of the gas or like a conveyor belt in your sunlight star simulations?
Yeah, so for this so-called sign-like stars, they're still like 10 times more massive than the sun itself. So we don't really see this large scale like circulating motions. What we instead see is that you have these plumes that are generated near the surface. They go all the way from the surface to the bottom. So this is like a different picture than this globally circulating blobs. I think, as you mentioned, this meridional circulation is mainly a phenomenon driven by the rotation of the star, which we don't have in our simulation.
Sorry. And then I was like, these are global slossy modes for the massive star. Is it like the same thing as slossy or it's a different?
Yeah, that's a good question. So slossy is kind of an instability you have in like supernova shock revival, where you like generate some instabilities near the surface of the shock. I think this is a different phenomenon, because in these massive stars I'm simulating, this instability near the surface is driven by kind of a radiation phenomenon, where it depends on the opacity of the surface. And I don't think that is the reason you have SASI in supernova.
Wonderful presentation, thank you. Galaxy scales, one of the big issues we have is trying to infer the total sort of populations of very distant objects based on the light they're expressing. And these phases, these giant, supergiant phases of stellar evolution are notoriously go up the works. To your predictions, are they like significantly different in luminosity than previous predictions for spectra or like these stages of stellar evolution?
So luminosity will not be different. What you get from this detailed simulation is that around this constant luminosity, you get some small scale variabilities. But I don't think that is something you can really see if you have like a stellar population. Yeah.
I guess my question is, how different is your math loss results compared to, like, say, the 1D mode?
Yeah, so in 1D, the basic thing is that we don't understand the mass loss mechanism of these stars. So what you do basically in 1D is that you have some empirical prescription from like observed this red supergiant. You have some observational constraint mass loss rate. And our prediction is similar in orders of magnitude, like about within 2 orders of magnitude uncertainty. But I think there are still some discrepancy, especially if you look at these sun-like stars I simulated before, that they don't have this large amplitude position. And there we actually don't predict any mass loss. So that is a problem, because we know these stars should have mass loss in observations. And there we still don't understand how they can drive a wind outside.
So you mentioned self-consistent creation of supergranulation in your simulations. I'm curious how those scales compare to what we see on the sun. Does it normalize by the size of the star, or is it like pretty different?
Yeah, I haven't done the calculation yet, but I think in general, what you expect from these stars is just that their local scale height on the surface is much larger than what you have in the sun. So you expect the granules and supergranules are also much larger than what you have on the sun. But I think whether that is just a scaled up version, whether you can just scale the length scales by the radius difference or not, I think that's something we need to.
So I know that compactness has lost a little bit of its favor in terms of being a predictor of remnant after, cell remnant. But this seems, I know that it's still getting worked on, I know after Connor's working on it. This seems like a really useful tool for studying basically using compactness of the star as a parameter space study. Are you planning to do that? Do you think, is there a reason that this couldn't be used for exploring compactness, in particular, its roles, stars evolving in the late stages?
Yeah, I think when you say compactness, you mean like this is a criterion to decide whether the star explode or not.
I don't see that they have changed a little bit of how they're defining compactness these days. Since last I dealt with that was a long time ago. But just basically how much of the star is in the core versus further out.
I think like the compactness. So what compactness is like a parameter to decide like how bound your core is, and depends on how bound your core is, you either successively explode as a supernova or you directly collapse into a black hole. And I think that is a phenomenon that to zeroth order approximation only depends on what happens inside the core of the star. So it doesn't care too much what happens in the envelope. So I don't think this will have a too large impact on the compactness of the star itself.
Yeah, I was hoping you could just connect this to the observations of Betelgeuse. So there was a few years ago there was that big Jimmy.
Yes.
It's always fun. It's this
yes.
We're seeing the pulsations, and then that was a big cloud and stuff that came off. And that's all back again. But what's going on?
Yeah. So my idea on Betelgeuse is just that you see these 4 different simulations I have, and 2 of them seems pretty calm. They don't have these great dimming events. And the 2 of them on the right-hand side, they seem pretty violent. So I think Betelgeuse is at some phase between these 2 extremes. So probably either it is like a 15 solar mass red supergiant that is not at the starting of its core helium burning, so maybe already kind of evolved somewhere in the core helium burning stage, where its luminosity start to climb up a bit to trigger some part of this instability, but not too much. This kind of also seems to be a fine-tuned parameter space that Betelgeuse is living in.
I have a question, yeah. About the mass loss again, I guess my concern is if your mass loss doesn't confirm with empirical relations, that raises a question about your boundary conditions. So would that affect the supergranulation or some of the convective stability that you mentioned?
Yeah. So as I said, the boundary is like so far away from the star. It's about 300 times larger than the star itself. So what you expect is that any wave that propagates or any shocks launched from the star will not reach the boundary until the end of your simulation. So in principle, the boundary should not have an effect on what's going on inside. So what happens, I think that this discrepancy between what the observed mass loss rate and our simulation is that we didn't include some of the necessary physics. For example, like people think you might have molecules, dust, forming the atmosphere of the stars, and you might actually have radiation pushing onto these molecules or dust to drive a wind, which is something we don't properly take into account in our simulation. And this is also kind of a hard problem to do.
Next thing cover.